did yesterday. So we said that an F and L to the B is weakly differentiable if what happens? If weakly differentiable if there exists a G in L to a B such that this G psi is inequality G psi in L2 is equal to minus psi gs, okay, f psi prime, okay, and this must be true for all psi in C naught AB, okay, just like it must be true. So in other words, for all test functions, if then this equality holds, then we say that G is actually the weak derivative of f. Okay, so this is what that is defined. And then we essentially reach to a space H1AB, okay, which is what it's a collection of functions from L to AB such that it's weak derivative. So whenever I'll use now prime, I'm going to mean weak derivative, okay, unless I mention it explicitly, okay, such that its weak derivative is also a square integral, okay. And then we said that there is a norm on H1. So in other words, the norm on H1 is what? It is defined as the norm of f norm is a square plus the norm of the weak derivative. So that's how we define norm. And then we said that with this norm, this H1AB is a Hilbert space. Okay? It's a Hilbert space. Okay? And this Hilbert space is continuously contained into what do you call CAB, in which all continuous functions, in which the functions for which weak derivative exist are basically also continuous. And this embedding, okay, is a continuous embedding. Okay. And what we mean by the continuous embedding means that there exists a constant C such that if you compute the infinity norm of f, okay, then it can be estimated by C times the H1 norm of f, okay, and for all f and H1. It is also something that we did. Then I wrote that we can generalize this. In other words, instead of H1, I can have Hn actually. Okay? So Hn is the space of functions from L to AB. In other words, it's a space of those functions which are square integrable and also their weak derivatives, higher order weak derivatives up to nth order, okay, are also square integral. Okay? This is what that is. And the norm on this H1, Hn, okay, norm on this Hn, in other words, the Sobolev spaces of order n. We call such spaces as Sobolev spaces. So that particular kind of Sobolev space is equal to what? It's equal to, and we define it as that it's a sum from R equal to 1 to n, not 1 to n, but 0 to n, and sum of, two norms. Squares is a slight degradation of what you did. Okay, square and into norm and okay. So in other words, same as the norm is same as the split, not same, but the analog to what we did in H1. So in H2, kind of another term will be added and so on and so forth. Okay. So inductively, I can show. So we kind of proved yesterday that this is a Hilbert space. I can show inductively that this Hn AB is also a Hilbert space. Okay? It is also a Hilbert space. Is it making sense? Why we defined all these actually? We defined all these because we want to solve, in some sense, what we call the Poisson problem. Okay? Well, the Poisson problem. So what's a Poisson problem? Let me formulate it, and let's try to have a discussion on it. Okay. And you will see that it's a bit different story than you are doing, for example, in differential equations, where you are not taking care about the functions. You just say, okay, because everything is in R actually, so everything is smooth, but we don't have such smoothness in either in LP nor in Sobolev spaces. So let us formulate the Poisson problem. So the statement is this. That for a given f in L2AB, given f in L2AB, we have following boundary value problem. Okay. So we want a U in some suitable space which satisfies the Poisson equation, and the Poisson equation is what? The second order derivative, for example, in one dimension. In two dimensions is going to be gradient actually, I'm going to talk about it also. So the second order derivative will give you this Fi. Okay? And where U should also vanish on boundaries. So this is what that essentially we want. So what we want? We want to find some suitable U in some suitable space, okay, which satisfies such a problem. In other words, if I differentiate that 2 times, so it should give you the minus f, and that U should also satisfy this equation. So now you're going to have, lots of problems. So the first problem would be, okay, what is the precise meaning of satisfying this equation actually? What is the meaning of satisfying this equation? Okay, so in other words, you want a U that satisfies this in weak sense, because all these are weak derivatives. Okay? So they should satisfy in the weak sense. This is what that you have to keep. Nothing is classical here. You need to keep this. Take away all classical things. Okay? So you have to understand everything in the terms of, in weak sense actually. Okay? So that satisfies this equation in weak sense. That's one of the things. So let me give the definition of the solution. Okay, before giving the definition of the solution, what do you think? What must be the suitable space in which we can have a solution for such a problem? What would be the most suitable?
C naught, sir.
Huh?
C naught.
C naught.
Last finish.
Okay.
H2
So
of
if you get a C naught,
H2A.
let me give you. If I have a C naught, so the C naught is important. Obviously, in other words, your solution should be continuous, and this must be there actually. So in other words, it should vanish on boundary. So the C naughtness is important actually. Okay. So you must have this. What do you call? Your solution should be C naught. And what else?
Double differential.
So it must be 2 times differential. So in other words, it should be in H2. So we are talking about H2 actually. Okay. We are talking about H2. Alright? But let me write this. What would be the meaning of this in weak sense? So what would be the meaning of this in weak sense actually? How can I write this equation in weak sense? Here's the thing. So I want a function u prime whose weak derivative is giving me f minus f. So now, what should be the meaning? So here, return to the definition. Return to the definition. So what we say for a function f, g is a derivative if f and g should satisfy this condition. Okay? So now I'm saying that the weak derivative of u prime is this minus f. So here is the question, what condition they must satisfy?
U prime dot if.
So they should satisfy u prime psi
Minus equal to minus.
okay.
Minus
No, not u prime psi, but
if.
minus f psi, and that must be equal to,
Minus.
Or some G.
because just think about it. So this f is like your g,
Yes.
and this u prime is like your what do you call f actually, okay, as in definition. So what condition it should satisfy? So minus f psi, inner product of minus f psi in L2 sense should satisfy what? U prime psi prime. Okay? And this must be true for all test functions. All test functions. Psi in C naught. Are you getting the point? What do you mean by that? What we have precisely do. Okay, what we have precisely do. So what we did basically that I formulated a problem. Okay, and I said that for a given f, okay, for a given forcing factor, for a given non-homogeneity, so this f could have some practical meaning. Okay, so for a given f, okay, I want a u, okay, in some suitable space that satisfies this boundary value problem. Okay, that satisfies this boundary value problem in some sense, and that sense is weak sense. Are you getting the point? Okay. Now here is the question actually that I would like to ask. What would be the meaning of solution of this problem? Okay. What would be the meaning of solution u for this problem? So I would say that the solution of this problem is a function u that vanish on boundary, first thing. Okay? Second thing, whose weak derivative, so in other words, the weak derivative of its weak derivative should give you minus f. In other words, the weak derivative of the weak derivative is actually minus f. So if so how can I write that the weak derivative of the weak derivative is minus f actually? So this means in a precise sense it should satisfy this equation. Because this is what that it is going to show. We are going to have a minus here.
Yes sir, but वो minus a कैसे हो सकती है?
Okay, so I can get rid of it from here. Okay. So in other words, the f, okay, the kind of f is the weak derivative of the weak derivative. In other words, it must satisfy, this in the product. So what we want to do, we want to show the existence of such u and also the uniqueness of such u, that such a solution exists. Okay? For every f actually. For every f, I can find a unique solution. Okay? Which satisfies this. Now here is the question actually. We haven't still settled that where that solution should exist actually. Okay? Where that solution should exist. So the first thing is that it must be in C01. It must be in C0 actually. So in other words, it should be continuous, which vanish boundary actually. So C0ness is coming from the boundary condition.
And we require 2 also.
Okay. So the first thing is, so you have 2 options. Okay, I'll talk about this H2 as well. So one thing is that, let's try to find an element of H2, which is indeed true actually, which satisfies this condition. But I want to look from this perspective actually. I want to look from this perspective. So in other words, in order to find a function, okay, that satisfies this condition, what condition must be satisfied?
It should be.
In other words, in order to find a u that satisfies this condition, where should be my u at?
C2.
C2.
C2 smooth.
No. I mean, if it is C2 smooth, it's a classical solution. We are not after the classical solution. We are in the weak sense. We want a solution in weak sense.
H2AB.
I'm saying H2 is too much to ask at the moment.
And sir, I have a confusion. H2 is defined on interval A to B, open interval. But you have A and B defined here. H1 of AB or H2 of AB, it's an open interval A to B, not on the boundary points. But this function is defined on boundary points also. So how this U can be in
No,
H?
but like I'm saying that it should be here. So when it is here, it must be defined on the boundary. So my claim is that your function should be in the intersection of something. The question is, what should be that intersection?
H2AB, big derivative.
How about if I say that this is same as H1AB? Why this should be? Think about it. This is the
Boundary condition was
So from here the boundary conditions are satisfied.
not really.
And for here, what you need, so in order to satisfy this equation, you don't need a second order weak derivative actually. You just need a first order derivative. So this is what the key thing is. Just think about it. Is there a second order derivative here of u? So why you need it? You don't need it. In weak sense, you don't need this. So you need your function in to be h1 so that you can have a u prime. You need it to be in C0 AB so that it satisfies boundary condition. And a u which is in h1 and C0 AB that satisfies this condition. Okay. So what we are going to have? So that problem, that u is going to be the solution of this equation in the weak sense. Are you getting the point? So We can go to H2, obviously. So this has a relationship with H2. I'm going to get into that actually. Okay? This has certainly a relationship with H2. It's a closed subspace of H2. Okay? But like this is what you want in precise sense. If you have a question, you can ask. Okay. Are we happy with this? Okay. So again, we want Poisson problem which satisfies this condition, this equation, and the boundary conditions. So in order to set, so when I'm saying that I want to solve this in weak sense, what I mean a function u whose weak derivative, or the weak derivative of the derivative is minus f, okay, in weak sense, okay, and that satisfies this boundary condition. Now I'm saying that what is the meaning of taking minus f being the weak derivative of the weak derivative? So it means that it satisfies. Okay. So if this is true, okay, then this equation is satisfied in weak sense. Okay. Now, in order to satisfaction of this equation, okay, you only need u prime actually. So f you already have, okay, psi are the test functions. So you only want the u prime to exist and satisfy such an equation. So for u prime, the existence of u prime and integrability, you need u to be in H1, and in order to satisfy the boundary condition, you should have this. Okay. Yeah.
So it should be weakly differentiable with a closed open interval and should be continuous with
Closed interval, and it should vanish on boundary. But H1 is more than weakly differentiability because it says that the function, in other words, u should be, if u is in H1, for sure, u prime exists. But it's not only that it exists, but it also integrable. This is what that you have to keep in mind. Are you getting the point? This is what that we want to do. I'm giving this space a name in order to make my life easier. I'm giving this space a name, and this space, okay, is H1.
Which not?
H1,
Sonata.
and I put a knot here. In other words, this knot is showing that whatever is going to belong to this space is going to be H1 and going to vanish on boundary, and they are defined on the interval. Okay. I'm going to get into the problem that, okay, how can I, so what do you think, what should be, so obviously if we have a new space, okay, so it's going to, a natural question arises that do we have any structure on this space actually? Okay, so back to the space, so can we have a norm on this? What should be the norm on this space actually? If I ask you? What do you think?
L2 no?
L2 no.
But 2 num is not computed in C naught. Right? 2 num.
So my H1, okay, H1 naught is H1 intersection
C
naught
naught.
actually, roughly. Okay. So what should be the norm on H naught if I want to try to have a guess? So here's a question. Here's the thing that you should have. So think about it.
In H1 num it is L2 num.
So in other words, it should satisfy the condition of
H1.
this. And it should satisfy the condition of this. Okay, so here is, so the norm of f in H naught 1 should be, so for example, I'm denoting it by H1 naught, should be equal to,
Norm of
okay, so H1, so it's f prime should exist, okay, okay, and it's what, okay, and it's L2 norm should, that be enough? Okay, I should write U so that you shouldn't confuse it. Okay? Does this make sense? So in other words, if a U has this thing finite, okay, can we say that it must be in H1 and C0? Okay, it should be in C0 because you are taking it from. Okay, it should be in H1. Okay.
And both.
So the U and its derivative. So for the U and its derivative, weak derivative, such an expression should make sense. So you have a norm over there. Okay. So what I'm saying is that this is sufficient. Okay. And this norm is called energy norm. This norm is called energy norm. This is a specific reason why we are calling it energy norm. Okay? Are you getting the point? Alright. Now you might think that, maybe the confusion point should be that, okay, why we have only this actually? Why you don't have a L2 norm of U? So I'm going to prove an inequality, and that inequality is called the Poincare inequality. And I'm going to answer this question. So Poincare inequality.
सर इसको हम कह सकते हैं ना H नॉट ऑफ 1 जो है स्पेस ऑफ सॉल्यूशंस टू Poisson प्रॉब्लम.
It's a potential solution. Okay, if a solution must be in this space, then it's going to satisfy the problem. But is it necessary that that solution exists? So this is what that we would like to prove that. So okay, so we identified the space in which if there is a solution, it should be. Okay, so asking the question of existence and uniqueness is a different discussion. We're going to get into that. Okay, so I'm going to prove so-called Poincare inequality, and it says that there exists C bigger than or equal to 0, okay, depending on B minus A, in other words, the length of the interval, okay, such that the U norm, okay, so L2 norm of U can be estimated by C times of L2 norm of U prime. Are you getting the point? For all U in H1 norm. Now did you got the answer? That why you don't need in this expression you don't need U to be norm of L2 norm of U should not be included here. Is it making sense? Why this is sufficient? Anyone? So see, when you are defining this, what you want to make sure? You want to make sure that this definition is true. In other words, so when I'm saying that F must be in L2AB, so in other words, this must be finite, and this must be finite as well. In other words, L2 norm of this must be finite. Are you getting the point? So when you are defining norm in this way, you want these conditions to be true. That's why you are defining it in this way. Are you getting the point? Okay. That you need